Okay, good morning. I hope that you have a good break. Now we start our lesson. Today we want to start a new and very exciting branch of mathematics, which is called the graph theory. And I think everyone agrees that probably the starting point of graph theory was this famous problem. I think there was I don't know, city in old Germany called Königsberg, or what they pronounce it. So you see a very simple picture of that city here. There were two islands, and there were 7 bridges connecting these islands to the main city. Okay? And I don't know, I read in the history that people on weekends probably wanted to solve this problem. They wanted to start from one of these points on the earth here in one of these parts and try to go through all these bridges exactly once and return back to the starting point. So that was the problem that they were trying to solve. Also, for example, I don't know, they wanted to start from here, for example, go from here, and I don't know, something like that. Okay, and then you see this is dead end. Okay, they were trying to solve this problem. To start from one of these parts, it is not important where, and to go through all these bridges exactly once and return back to the starting point. So that was the problem, and people probably apparently were quite busy to solve these problems. And then Euler came in and tried to model this problem in a different way, in a mathematical way, and then tried to solve this problem. And of course he realized, for the reasons that is not that hard, we will probably reach to it in this course, and the answer was negative. Of course, that was not very good that Euler did this, because people lost their hobbies on weekends, and probably, I don't know if there were any cinemas or something they could go and enjoy. But anyway, they realized that probably, I don't know how many people believed Euler at that time, but yeah, that was the end of this problem, and actually that was the start of a very powerful branch of mathematics called graph theory. Okay, so the idea behind this problem was simple. Yeah, what he did actually, he actually said that, okay, I think every one of you agrees with me that it doesn't matter where, for example, on this part, it doesn't matter if I start from here or I start from there. If I can solve the problem by starting from here, then apparently I can solve the problem starting from there as well. Yes, so it is clear that it is not important where to start with. If the problem can be solved with this point for starting, definitely it can also work for this one, it can also work for this one. So that was the idea behind the solution. So he said to himself that, okay, because apparently all the points lying on this area, a region, are actually equivalent for me. So let me make the problem simpler and put one single point to represent this piece of land here. Okay, so for example, we can put A here. Now let me change the color. So for example, we can put A here and say that, okay, this point A is supposed to represent all this piece of land here. Okay, and then we can do the same thing here. So it doesn't matter if I choose this point or any other point here. So let me just choose this point. So for simplicity of drawing for later, let me just for example choose this point B. So if I ask you what is A is a representative of this piece of land, and B is a representative of this first island, and I can choose another point to represent the second island. So let me call it C, and then I will have another one here representative, I will call it D. Okay, so, and he said that, okay, instead of looking this problem in this way, let us try to simplify it in this form. So we can draw this, for example, let me, from going from here to this is equivalent to something like that. You see, I draw a curve or whatever connecting these 2 points, and I can draw another curve passing through this bridge 1 and connecting itself to point A. Yes, and then I can do the same thing here. I'm passing through these bridges, yes. So, and then I would say I have this one, and there is another path or walking way connecting these two. And then for C to A, I can have this situation, yes. And then I have this one. Okay? So I think it's much simpler because you push away these distracting things and just focus on the real thing, okay? And I hope that you agree with me that instead of making this graph, so this is actually called a graph. You see, there are some nodes here, and there are some lines, or in this case, curves, connecting these nodes. What you see here, if you do not see at the main picture, what is left for you is called a graph. And of course, hopefully you agree with me, the real form of these curves are irrelevant. Yes, for example, here it doesn't matter if I go up and down and then go from here to here. It doesn't make any difference. And now let us see how we can translate this problem, the original problem, to this problem. So he said that let me simplify this. So I have some dots A and B. Let me write B here, and then I have D here, and then I have C here. I realize that two curves, two roads or whatever connects A and B together. So these ones that I have drawn here are this one and that one. And then there are two roads connecting B with a D. So I forgot to write D here. So this is this one. So these two that you see here are this one and that one. And there is only one between B and C connecting them. So I draw this one. And then if you see, there is one connecting A and C. Of course, here, for the purpose of the problem, it doesn't matter if I draw it as a curve or if I draw it as a straight line between these two. And another one is between D and C. So you see, this is a model that simplifies the problem a lot. So instead of keeping yourself busy and walking a lot, actually, if you don't care about doing exercises, you can sit behind your chair and try to solve this problem, yes? So the problem is that, is it possible? I state a new problem. I want you to feel the connection between these two and see that these two things are actually equivalent. The question is that Euler was posing this question to himself. Is it possible that I draw this graph, okay, with one pen stroke, starting, and then I am not allowed to redraw one of these edges, one of these sides more than once, and return back to the same point? Yes. So if I can draw this picture, what you see here, with one pen stroke, starting from any one of these nodes, returning back to the same node, make sure that you are not passing through any edges more than once. If I can draw this on paper, then using that I can tell the people how to move around. That would be the solution to that problem. But if there is some reason that convinces me that I cannot draw this shape with the conditions that I just mentioned, it means that we cannot solve this problem. Just I want to wait a little bit for you. Is this connection clear? Is the connection between drawing this graph on a piece of paper and this practical problem moving around the city from bridge to bridge, from point to point, are equivalent? Do you feel the equivalency of these two problems? Everyone agrees? Okay, good. So this is the problem, and that is probably people say in history this is the starting points of graph theory. So this is a very simple problem. People probably you don't think that mathematics has something to do with solving these kinds of problems. These are just puzzles or riddles in the, I don't know, some magazines you want to make yourself busy a little bit. But yes, there are some very deep theorems going on, and they are studying, the mathematicians have studied this a lot, and there are many applications to what we call graph theory, especially in computer science and mathematics itself. So there are many. In chemistry, I don't know, for example, if you draw these molecules, you have seen them in chemistry, for example. I forgot the name. What is the name of this combination? CH4. What's that? Okay, is it ethan or methan, or I don't know exactly. Okay, anyway, but this one is also a graph. You see the nodes are the atoms, carbon atoms and hydrogen atoms, and these connecting them. So this is very similar to a graph. And then if you know properties of the graph of this molecule, so you can conclude something about the molecule itself. So I mean, there are many applications of graph theory. Okay. Okay. Now another important thing that you need to understand here. Before that point, people mostly were, if they wanted to draw a shape, mostly they were thinking geometrically. Okay, so in geometry it's important. So this picture is called a triangle, but this picture is not called a triangle. It's something else. I don't know what's the name of it. There is no probably name for this. So in geometry, these two shapes are completely different. Okay, and even this triangle, if I want to keep the triangle, I can write the triangle in this way. I can just do the triangle in this way. These are triangles. All of them are triangles. But they are not the same object geometrically. They are different. But you see that here, this graph that I drew here first is different from this one. But for the problem that I am studying, they are equivalent. So you see that there is also another branch of mathematics involved here. It means that the real sizes between the nodes and the real shape between the real shape or the real curve that I connect two nodes with that together are irrelevant in this context. It doesn't matter if I draw this graph, for example, in this form. Might be this also works, yes. I don't know. And then I will give this one, and I will do this, and I will do that. I don't know. I make this one the same and this one the same. As far as if I can draw this graph with the conditions that I told you, I can definitely draw this graph with the same conditions. But of course, these are two different shapes, yes? Geometrically, they are totally different. For example, what is important in geometry? One of the things important in geometry is the distance between 2 points. So for example, the distance between these 2 points, it might be different from the distance between these 2 points, or I don't know, I can make it even shorter, okay? But the distance between these 2 points is this one, is different from the distance between these 2 points. So it's very easy to realize that geometrically, these two shapes are completely different. But we say topologically, they are equivalent. So there is also another branch of mathematics. It's called topology. Yes. So from topological point of view, these two shapes are the same. Because in topology, what is important for us is not the real shape between the points. It's important, the connectivity is important, and if I am actually cut one of these edges and connect them. So so you can assume that as you can consider these as rubber bands. As far as I can change these rubber bands in any way that I like, but I need to be sure that I don't tear them two parts. I don't tear them apart. Okay. In that case, what I get is topologically equivalent to my main shape. So that's also some kind of starting of a very active and very powerful branch of mathematics, which have a lot of applications even in physics and other parts of science. So this is very important. So for the graph theory, you need to understand the real shapes are irrelevant. What is important are the nodes, the number of nodes, the number of these lines, which we will call edges, and the connectivity between these two. For example, here we see that A and B are connected. But for example, A and D are not directly connected. For example, if I draw another line here, then I will get a new graph, because in the previous graph A and D were not directly related. But if I add another line, I am making A and B directly related to each other. Okay, so then I am facing a new graph. Okay, so that is the history of the graph theory, and later in the course we will learn that the answer to this puzzle is negative. So from mathematical point of view, I can convince you, hopefully, that this is not possible. For example, another simple one, let me just do something here. For example, I don't know how many of you try to draw this picture. Okay, so let me make it better. So for example, if you want to draw a square with a cross inside it, but of course you saw that I raised my pen and put it back again, and I was able to draw this. So you can also see that, is it possible? Let us make it simple. Do you think that you can start from one point and drawing this? By the way, in graph theory, it's important to make these dots visible. Okay, so I am not putting a dot here. Okay, so it means that I am not considering this as a vertex. We will talk about these things later. So can I draw this with one pen stroke and return back to the same point? Or can I draw this with one pen stroke and do not return to the same point? I want to relax the second limitation. Okay, I don't know, you can try to work a little bit on it. For example, one way is here. I drew it here. If I go here and then I go here, this is a dead end, because I haven't drawn this next diagonal. But the problem is that if I want to start drawing that diagonal, I have to actually go through this edge once more. Okay, so you see that you can try to work a little bit on for this one yourself, to see that if you can draw this one with one pen stroke, with the condition that you're not allowed to move on any edge more than once. And the same story, if you know the theorem behind that, you immediately realize that this is impossible again. But for example, what about this one? If I let me just draw this in this way. For example, let us draw this diagonal here, this one here, and then let me add one triangle on top of that. Of course, I did it with moving my pen from the paper. So is it possible to draw this one? I'm just trying to motivate you. It's not simple at all to answer these questions. The only thing that you might think right now is probably to do some trial and error, which is completely good, and you need to be good in it when you want to study graph theory. But for example, there is a theorem that you can draw this, but you are not able, if your if you want to return to exactly the same point that you started with, this is not possible. But if you want to draw this with one pen stroke and go through each edge exactly once, but return to any other point, this is possible. And this is telling you, again, the theorem tells you that you have to start with either this corner or that corner, that there are odd number of edges involved. So here you see there are 2 edges involved here. There are 4 edges involved. All of these numbers are even. And that theorem guarantees. So that's a very nice theorem, yes. This is very interesting to see how mathematics can be helpful in any way of abstract thinking, yes. So let me, if I remember how to draw it. For example, let me start from here. I go up there, here, and here, and then I go here, and I go here. No, this is a dead end, yes? No, that's good. I go up there, I go here, and then I go there. So you see, but I was not able to return back to my starting point, but I was able to complete this diagram. Okay? And I covered all the edges exactly once. And the theorem actually predicts, don't waste your time, you will not be able to return back to the same point and having those conditions that you want to cover all edges exactly once. Okay, so these kinds of problems you should expect to see in graph theory. Any questions so far? Okay, so you see that this idea was very powerful. Instead of looking at the whole piece of land, I took just one point as a representative. Of course, working with one point is much easier to imagine unnecessary information in this problem, yes. All these piece of land is actually unnecessary information. What is important for me is just one single point. These kinds of simplifications are actually very brilliant ideas. Okay. So in graph theory, usually we have some objects and we want to look at the connectivity between those objects. Okay, so I will try to give you more examples here to see how this will go. Alex, Emma, Lucas, Olivia, and Sophia go to the same school. We know that Alex is friend with Emma and Sophia. Lucas is friend with Emma, Olivia, and Sophia. And Olivia is also friend with Sophia. So you see, when I read it as an English sentence, it's usually a little bit hard to keep track of these friendships. But if I draw a diagram, okay, how? So here in part 1 I have asked you draw a diagram that represents being a friend with relation among the people stated above, okay? Which is more illuminating for me. By looking at the graph, I immediately realize which person is friend with which person, yes? But of course I can detect the same piece of information by reading the sentence over and over again. But I don't know, from evolution point of view, probably our brains is more adapted to see, to visualize pictures than abstract notions, of course. So this is also very helpful here. So let us, for example, what can I do for part 1? I can, for example, put a point anywhere in the plane and call it capital A for Alex, and then capital E for Emma, and then capital L for Lucas, and then Olivia O, and then Sophia. Okay, and then I read this information, and then I connect the people who are friends together with each other. Okay, so for example here, when I read Alex is friend with Emma and Sophia, I decide to connect Alex with Emma and Sophia. Of course here, let us do it with the straight lines, even though you agree with me, a straight line is not, being straight is not very important here. Okay, and then let us read the second piece. Lucas is friend with Emma. So by this one I realized that Lucas is friend with Emma, so I connect these two together. And then with Emma, Olivia and Sophia. So Sophia and Olivia, yes. So I connect them. I don't know why. This is the feature. I don't want to turn it off right now. It takes time. But you don't need to put this region colored, okay? And then Olivia is also friends with Sophia. So there is another edge that I have to connect, yes? Okay, so that's at least good. So this I hope that you see that by looking at the graph, you can extract the information much more quickly and much more organized. So this is the friendship relation among these people according to the information provided by the problem. Okay, what do you think about the second one? Draw a diagram that represents not being a friend with relation among the people stated above. So do you think, what should I do now? If I want to draw a diagram showing not being a friend with. Of course, I am assuming that friendship is a mutual relationship. Yeah, exactly. That's clear. So that's also, of course, this is not part of your lesson, but that would be called a complement graph. So this, what you see here, of course, forget about this shaded region. You don't need to shade them. This is your graph with these nodes, okay? And then, of course, if I draw, so here, I know that Alex is friend with Sophia and Emma. This is the only piece of information here provided for me. So it means that Alex is not friend with anyone else. So if I want to consider on not being a friend with relationship, so what I need to do, I need to draw a line from Alex to Olivia, and I need to draw a line from Alex to Lucas. That's it. So these two, this gray piece, these two gray edges are part of that new diagram. And then I go to Emma. Emma is already friends with Alex and Lucas, yes, but she is not friend with Olivia, so I draw another diagram here, another line here, and she is not friend with Sophia. Okay, and then I go to Lucas, so I considered everything for Lucas already, and then when I go to Olivia, that is also being considered, and when I go to Sophia, that's also being considered. So if you consider this red parts, this is the graph of friendship, and if you consider this part, this is the graph of not being friend. This graph represents not being friend, and the first graph represents being a friend. So I hope that, of course, I did them in one diagram, but if I draw separate diagrams, it's easier for us to extract the information instead of reading the question, the problem over and over again. Okay, so 1 and 2, actually, this is considered 1 and 2 in one of them. Okay, for example, let us consider another problem here. A company has announced 4 job vacancies, J1, J2 up to J4. 5 people, P1, P2 up to P5, have applied for some of these jobs. The owner of the company has access to the following information. P1 can handle only J1 and J2 and J3. P2, person number 2, can handle only job number 3 and 4. Person 3 can handle only J2, J3, and J4. P4 and P5 can each handle only J3. According to this information, can the company fill in all 4 vacancies? If yes, in how many ways? You see, again, I have a lot of data. If I want to keep track, it's better to draw a diagram to be able to keep track easier. Yes? For example, what can I do? I can, for example, put some dots representing people and put some dots representing jobs. Okay, so for example, I can say that this is person, let me write J1, job 1, and then job number 2, job number 3, and then finally job number 4, yes? And then I have 5 people, so let me give some space. I don't know what's going to happen. So P1 and 4, this is P2, person 2, and then I go 4 units. Person number 3. I don't need to be careful in drawing, but of course it's better to be organized always. Yes, so P4, and then here I can draw P5. So I have 5 people and I have 4 jobs. Okay, but now let us start connecting points. What I know that P1 can handle only J1, J2, and J3. Yes, so what can I do? I can draw a line from P1 to these jobs. Okay, this is a better way of seeing this information. Yes, so P1 is connected to J1 and J2 and J3. So by looking at this, I immediately understand what is the first piece of information. Okay, it's easier for our brain to visualize than to read. Okay, and then we go to P2, handle can only jobs 3 and 4. So this means that I don't know if this is a good idea to change the color all the time, but let me change it. So P2 is connected to J3 and J4. So J3 and J4. So I will connect these to that. I will also connect these to this. If I am making any mistakes, please let me know immediately. Okay, and then P3 can handle these 3 jobs. So let me change the color again. So P3 can handle J2, J3, and J4. So J2, yes, J3. Oops, this is a bad feature now. I didn't mean that. Anyway, J4. So I don't know how to turn this off immediately. I've forgotten. Okay, and then let us read P4. P4 and P5 each can handle only job number 3. So let me draw this with a different color. They can only handle job number 3. Yes? Okay, so this is the graph that I get here. Forget about these colored regions. It's not important at all. The only important are these lines and the nodes. So hopefully you agree with me. This is a better way. You can immediately answer any questions regarding those pieces of information provided for you in this problem. Yes? Okay, now can you try to see, is it possible with these conditions, is it possible for the owner of the company fill in all these 4 vacancies? And if that is a yes, in how many ways they can do that? Of course, the answer is not evident immediately, but let us try to see what we can do. If, yes? May you speak louder, please?
Should it also include ways where we include people who are unnecessary to the solution?
No, I'm just assuming that this is the only option available for the company if they want to hire someone. For example, assume that they have waited for a long time and these are the only people that they can be hired for these particular jobs. I don't know, is that your question?
No, my question is it okay if they also hire unnecessary people?
No, not unnecessary, because job 1 should be filled with 1 person, job 2 which would be filled with 1 person. So you need to decide one of these people. Assume that you have waited for a long time, these are the only candidates and you want to fill in the jobs.
So they are not allowed to multitask?
No.
Okay.
Yeah, I should have mentioned that. Yes, that's not possible. Okay, so where is a good starting point to analyze this problem? There is a best way to start with. Which job is better to think about first?
Job 1.
Job 1, because if I want to hire, if I want to fill in these jobs with these people, then I can realize, then I can decide, of course, if this is useful or not, but I can realize, according to this graph, I immediately realize, of course, it was possible to read these information again and again, but it is immediately evident, agree with me, hopefully, that this job 1 by this diagram is clear. This can be only handled with one person, and that is person number 1. Okay? So if I want to do that, what should I do? If I want to do this, then I would say that, okay, J1 should be occupied with P1. And as you said, because there are no multitasking assumed here, so it means that, and I need to clean this. So it means that P1 is now out of my list. And of course, I don't care about the other connections because already job 1 is being filled with J1, yes, with person 1. So I clean all these now pieces of information related to J1 and P1. And now what is left here, then again, it is clear what to do now, yes? Which job I need to think right now? It's clear J2, because if I give J1 to P1, which was the only option available for me, then there would be one option left for job number 2, and that is P3. Yes, so it means that if I want to fill in these jobs with these people, then I have to give J2 to which person? P3. Okay? And now I need to clean to get rid of the extra pieces of information. So person P3 is already employed, job 2 is already filled. Okay, it's hard to clean all these things without affecting, but you can imagine, yes? Yeah, so yeah, you can imagine something like that. Don't look at these two parts. Okay, but then immediately again becomes something clear. Then it means that for J4 there is only one person left, and that is P2. So what I have to do for J4, I have assigned person number 2 to it. And when I did that, what I have to do, I need to get rid of these irrelevant pieces of information now. Yes, and now what is left for me? Job number 3 can be occupied with either person P4 or person P5. So this means that J3 should be occupied either with P4 and then P5. So this means that if I want to employ these people, if I want to fill in these jobs with these people, this is inevitable. I don't have options. But for job number 3, probably I can arrange another more restrictive interview or whatever, because I have an option available for choosing the person suitable for job number 3, and that is either P4 or P5. Okay, so you see, I hope that you agree with me that this is a simple way of thinking about the problem. So I would say that there are two different ways that I can do this. So job 1 should be filled with P1. Job number 2 should be filled with person P3. Job number 3 can be filled with P4, and job number 4 can be filled with P2. This is one way of solving the problem. Another one is I employ person 1 for job 1. For job 2 I choose person 3, but for job number 3 I choose this time person number 5, and for job number 4 I choose person number 2. So this is another way of doing that. So you see, this is not something very strange. I'm just doing graph theory to visualize easier. That's it. I wanted to give you some motivation that graph theory can actually be used very naturally in the problems that you might think even you don't know, even if you haven't heard about the graph theory, might be this idea comes to your mind to draw the diagram to see what are the connections. Okay, so let us now start formal graph theory. This part is not mentioned in the graph. I just want to understand that in mathematics, graphs and the abstract definition of graphs are a little bit different. They are interconnected, of course, but yeah, just be patient a little bit to see this abstract notion of a graph. Okay, so the formal definition of a simple graph, I will talk why we use this adjective symbol later, simple. So here, let V be a finite non-empty set. So imagine that you have a finite set which is not empty. And let this capital M be the set consisting of all two element subsets of V. So what does it mean? For example, if V is AB, okay, then M is the set consisting of two element subsets of V. Okay, but there is only one, so it means that I have to write A, B enclosed. Okay, if I have V with three elements, then what is M? M is, for example, AB, and then I have AC, then I have BC. So this is what I mean. This is the set consisting of all two elements subset of my set. Okay? Then the ordered pair V and E, okay? E is a subset of M. Okay? Okay, let me try to show the example for you. It seems probably a little bit strange. So if I give you a set V, what is M? M is the set consisting of all two element subsets of this V. So what if I ask you give me a two element subset of V, might be some of you give me this. I write it as the first element here. Some of you might give me this. I also write that. I want to consider all possible two element subsets of this V. Yes? So I have written all of them here. And then what I do for another set E, I choose a subset of this. For example, I have chosen this one. I put it here. I have chosen this one. I have put it here, and I have chosen this one, and I have put it here. Then the original set V and this set E is called a simple graph. So this ordered pair, whose components are sets, is called a simple graph. So you see there is no notion of a diagram at all. If you want to understand graph theory from abstract point of view. So if I ask you what is a graph from abstract point of view, you would say that a graph is a two component element. Both components are sets with these conditions that I described for you. V is a non-empty set and a finite set, and then E is any subset from all two element subsets of V. Yeah, it might be a little bit convoluted, but the idea is very actually simple. But then we will connect this idea to diagram. So if I want to draw a diagram, you see the notion of function. Do you remember function was an abstract rule? When I say f of x is equal to x squared, there is no notion of graph here in the definition of a function. But you can draw a graph that represents this function, say this graph. So these are two different concepts: a function, the graph of a function. even though in your book the graph is always the diagram, but I just want you to, this is just half a page. I want you to understand from abstract point of view, a graph is not a diagram. A diagram is something that you associate with your graph. Okay, so for example, later, if I want to visualize this graph, what I do, I put 4 points, A, B, C, D, and then I connect A to B, I connect A to D, and I connect B to C. So this would be the diagram representing this abstract graph. Okay, and don't worry, all time we will talk only about the graphs like this. I draw a diagram for you. That is called a graph. Okay, but I want you to know from a little bit abstract point of view, and this remark is also important. Since the empty set is the subset of every set, E can be the empty set, but V is never the empty set by definition. So if I go back to the definition, if I go back to the definition, I have emphasized that V is finite and non-empty. Okay, and then so this is by definition V cannot be empty, but I have mentioned that E is a subset of M, and you know that in general E can be the empty set. What happens if I choose the empty set? If you don't mind, let me stop a little bit here. I don't know, this speaker is making noise. Okay, sorry for the interruption. So let us now go back here. So here I told you that by definition, this first set that you choose is supposed to be an empty set, a finite set and non-empty set. But I have mentioned that E is a subset of M, and in set theory we learned that the empty set is always a subset of every set. So in principle, E can be the empty set, but not V. Okay? Let me also read the other parts. The set V that we write first is called the vertex set of G, and each of its elements is called a vertex of G. The set E is called the edge set of G, and each of its elements is called an edge of G. To emphasize, usually when dealing with more than one graph at a time, the vertex set and edge set of a graph G is denoted by V of G and E of G. Okay? And then I told you that you put them in an ordered pair and call it a simple graph. So you see, a simple graph is a really abstract notion. The diagram is something that we associate with a simple graph to understand it better. Okay, exactly like a function f of x equals to x squared, we draw the graph of that function to understand the properties of the function better. But when I want to talk about functions, I really don't need to start for drawing the graphs. Yes, I start with the function first and then associate a geometric object to my graph to understand the graph better. That is the same story here. But don't be worried about it. I just want you to know this as an extra piece of information if you are interested in a little bit more abstract way of thinking. Okay, now everything else you need to know. Okay, so adjacent vertices, vertex incident with an edge. These are some terminologies that you need to know. Okay, so let me repeat this example once more quickly. So I have this set. It is a finite set. It consists of 4 elements and it is non-empty. What is M here? M doesn't have any role here, but I just want to write it here to see all the options available for me. I want to write all possible 2-element subsets of this set and write them here. And then I will choose a subset E of M, whatever I like. Then the ordered pair whose first component is this set and whose second component is this set is called a simple graph. Okay? And later we will associate a diagram for this by putting 4 nodes A, B, C, and D, and connect them if they are appearing as the elements of one two-element subset here. So you see A and B should be connected, A and D should be connected, B and C should also be connected. This would be a diagram that we associate with this abstract graph. That's it. And then now I am talking about this definition. Okay, look at the definition. Let G be equal to V and E be a simple graph, and let U and V be vertices of G such that U and V belong to the edge set E. Okay, then the vertices U and V are said to be adjacent. Exactly here. So here this vertex A and this vertex B are adjacent because there is a edge connecting them directly. But for example, A is not adjacent to C because there is no edge connecting them directly. So that's a very simple idea. Okay, and in this case we say that the vertices U and V are incident with the edge U and V. These are the words that you need to know in graph theory. Okay. Moreover, if there is no matter of confusion from now on, the edge, this, will be simply denoted by UV, VU. So in graph theory, when you see UV, it is not a product of U and V, because U and V are vertices. We cannot multiply them. So instead of writing this with unnecessary curly brackets and comma, we just simply write UV or VU. So for example, if I want to make this a little bit smaller that you can see, so here, if I consider this graph again in example number 3, instead of writing the edge set a little bit complicated like this, I can simplify it to it, because instead of this one I can simply write AB, instead of this one I can simply write AD or DA, it doesn't matter, and then instead of this one I can write BC. So that would be the edge set. And then I made a little bit of mistake because I am talking about the order and size without defining them first. That's a little bit annoying. Okay, I will come back to this. Let me just talk about this. I have talked about this later. That's my bad here. Order is the number of vertices. Size is the number of edges. So if I ask you what is the order of this graph, you count the number of elements in the vertex set and you say 4 is the order. And if I ask you what is the size, you count the elements in the edge set. So you see I have 3 elements, so the size is 3. That is unfortunate. I have probably confused myself. I should talk about this first and then write this. Anyway, the vertex B is adjacent to both vertex A and C. Why? Because you see that I have AB here, so it means B and A are adjacent. We have BC here, so it means B and C are adjacent. But A and C are not adjacent because I do not have AC in my edge set. Okay, now let us also talk about the diagram of a simple graph. So from now on, again, we come back to the book. Okay, these terminologies you need to know, they are in the book, but always you work with diagrams for graphs, not abstract notions. So let BG be a simple graph. A diagram that is obtained by drawing a dot for each vertex and joining 2 of these dots by straight or curved line, if the corresponding 2 vertices form an edge, is called a diagram. You see, I haven't written the diagram because you have degrees of freedom. Let us, for example, consider it here. Example number 5. Let G be this one. V is given to you, is also given to you. Draw 2 diagrams for G. So what can I do? For example, I can choose a point, call it A, another point B, another point C, and D and E. I just put these points because I have 5 vertices here. But then I realize A and B are connected, so I connect them. And then B and C is connected. C and D is connected. D and E is connected. Yes, and E and D is connected. E and A is connected. So this is one diagram that I can draw. It's extremely important to make these dots visible. This is in graph theory. Be careful, by the way. If I draw this, okay, if I ask you how many edges are there, what is the answer?
3.
No, there is one edge. Okay, so this is one. You might say 1 and 2. I don't know why you said 3, but or you said 2. I don't know.
I thought.
Yeah, but anyway, it might be confusing that you say 2, but be careful. If I mean there are 2, I have to put a dot visible here. Okay, if the dot is not visible there, you are not allowed to count this one and this one like geometry. Yes, so if you don't have that dot there, the only information that you get here is this vertex is connected to this vertex. It doesn't matter this graph and this graph and this graph are all equivalent, you see. This is why we talk about a diagram instead of talking about the diagram. So if I ask you to draw the graph of this, you can draw it in this way or this way or that way or that way. All of them are equivalent. So be careful about these things. We will come back to these later, okay? So let me clean it here. This is one way. When I ask you to draw a diagram for this, if you draw like this, that's completely okay. I don't know, might be, let me change my color, might be you write A here, B here, C here, D here, E here. This is also possible. Then what is this one? I have A, B, so I have to connect A to B, and then I have B to C, then I have C to D, then I have D to A, but then I also have A, E to A, so that's also correct. So you see there are many degrees of freedom. In graph theory, there is no difference between this graph and that graph. Because what is important is which vertex is connected to which. So for example, by looking at this graph, you see that A is adjacent to B and E. That's it. And if you go here, A is adjacent with B, there is a direct edge between these two, and there is a direct edge between A and E. And if you consider all these vertices, you will see that the neighbors are exactly the same. So what is important from adjacency point of view, this information that I get from this picture is exactly the same information I get from this picture. So in graph theory, these two shapes are completely equivalent, even though in geometry they are completely different objects, different shapes, yes? From topology point of view, these two shapes are again the same thing. If I assume that these are rubber bands, okay, and these are the, I don't know, nails, I can take the nails and just move them around without tearing these rubber bands. I can make this shape. I think it's easy to imagine it, okay? So this is two diagrams that I have drawn. You can draw infinitely many diagrams. All of them are equivalent, of course. Is that understandable? Good.
Yes.
Okay, good. Let us now solve this problem. Let G, V and E be a simple graph where the vertex set is given to you and the edge set is also given to you. We want to draw a diagram for G. So you need to understand how to read these pieces of information. So the vertex set is completely clear. In the vertex set, I have 7 points. So I have to put 7 dots representing these elements. So what I do, I put, for example, you don't need to be very careful. So you just write it in a way that you have enough space if you want to connect them. So let me start clockwise, for example. 1, 2, 3, I don't know, 4, 5, 6, and 7. So this is just some random dots that I put on the plane. And now let us read. It tells you that A and B is an edge. If A and B are coming from this vertex set, but there is a condition to that. The condition is that if you multiply A and B, it's divisible by 3. In that scenario, I connect A and B. Otherwise, I do not connect them. So that's it. So for example, do you think that I should connect 1 to 2? I multiply 1 and 2, it becomes 2. Is 2 divisible by 3? No. So 1 and 2 are not connected according to this piece of information. Okay, but what about 1 and 3? Are they connected? The answer is simply yes, because if I multiply 1 and 3, it becomes 3, and 3 is divisible by 3, yes? So I connect them. You immediately realize that 1 and 4 are not connected, 1 and 5 are not connected, 1 and 6 are connected. If you don't understand, please let me know. I think the idea is very simple, yes? Okay, so don't be in a hurry. I finished the task with 1. I move to the next point, 2. Okay, I don't need to consider 2 and 1 because I considered this relation when I was considering 1 and 2. So it means that I need to go forward, not backward. Okay, so should I connect 2 and 3? Yes, because 2 times 3 is 6. 6 is divisible by 3. So I connect this one. Should I connect 2 to 4? The answer is negative. 2, 5, no. 2 to 6, yes. 2 to 7, no. This feature is actually killing me today. Okay, anyway. Then we go to the next one, 3. What do you think about 3?
It will connect with everything.
With everything, yes. So I have already considered 1 and 2, so I don't need to consider them again. But it's clear because 3 multiplied by any number is definitely divisible by 3. So we don't need to think. I need to just connect this to everything. Yes. Okay. And now when I go to 4, I only connect, of course I have connected to 3 before, but I just connect to 6 as well. And then I go to 5, I just connected to 6. And then I go to 6, it's already, so what is left for 6? You see, I have also considered 6 times 7. And then when I go to 7, that's it. So this is the graph. Forget about these colored parts. You don't need just the nodes and the edges. That is one possible graph diagram that you can draw for this graph. Of course, it is clear that I can choose these points on different points on the plane. Then I will get apparently a different diagram, but those two diagrams are equivalent in graph theory. Okay, this was my bad here, so let me just mention it here. So I formally defined order and size here, which I already told you. For a graph G, the number of vertices is called the order, so don't get confused. The number of vertices is called the order, and the number of edges is called the size. Order, this is the standard usually notation. We denote it by P. The number of vertices of a graph G is denoted by P of G. And usually if we are dealing with only one single graph, we don't need to bother to mention the name of the graph. We simply write P. And the total number of edges is called the size, and it is denoted by symbol Q. For example, let me make sure. Can you tell me what is the order and size of this graph here? What is the order?
Five.
So order is 5. 1, 2, 3, 4, and 5. The order is 5. So let us write order is 5. What is the size?
Isn't it also 5?
Let us check. So from A to B, 1 edge. B to C, 2. Yes. C to E, 2. 3. Yes. Don't consider this because this is not a vertex. If it is going to be vertex, I have to make it visible. If it is not, it means that this is not called a vertex. Okay, so be careful about this. Usually in geometry, this is a point, the point of intersection of these two lines. But there is no point here in graph theory unless I make it visible for you. Okay, so this one is 1 edge, 2 edge, 3, 4, and 5. So yes, you are right. So the size is also equal to 5. Any questions here? Okay, so let us see how much is left here. Yeah, we can finish this one as well. This is easy. It is also possible, this is an important remark, it's also possible to have more than one edge connecting a pair of vertices. Do you remember the one Euler actually drew here? So for example, between these two vertices, I have more than one edge. I can have even more, yes? This is not allowed for what we call simple graph. In simple graph, this situation doesn't happen, okay? But there is another type of graph, is called multigraph, okay? It is possible to have more than one edge connecting a pair of vertices. Such edges are called multi-edges. It's also possible to have an edge that connects a vertex to itself. Such an edge is called a loop. Yes? A graph that contains a multi-edge and or a loop is called a multigraph. Okay? So the graph that Euler considered to solve this Konigsberry bridges problem and the following graph are examples of multigraphs. This is a multigraph. You see, this is a multi-edge. This is just a simple edge. But this is what we call a loop. Yes? And you don't need to draw a complete circle. You can just draw it like that. It doesn't matter. Okay? And this is also important. If I ask you, don't think that this is some mistake here. This is what we call later an isolated vertex. Okay? But that is a vertex. If I ask you what is the size of this graph, what is the answer? You need to count all the vertices, even this one. So 1, 2, 3, and 4. So the order of this graph is 4. But what is the size of this graph? You need to count all the edges, including multi-edges and loops. So what is the size? 1, 2, 3, 4, and 5. So let me write here. Of course, I haven't asked for this, but Q is 5 and P is 4 for this graph. Okay, so let me consider this one here. Which one of the following graphs, if any, is a multigraph? Do you have any idea here? Do you see any multigraph here?
G1 is a multigraph.
Yes.
Is it G2?
No, G2 is not a multigraph. Be careful.
Yeah, because,
G2 is a simple graph. But G1 is a multigraph. Why? Because in G1, if I consider this vertex and that vertex, there is one direct edge from here to here. This is one direct edge, and there is another direct edge going up there. So between these two I have two edges. So it is not a simple graph, it's a multigraph. But when I go here, if I ask you if this is A and this is B, this semicircle is the only edge between A and B. You cannot say that another edge is this one. No, this is not one edge, because now I have this dot here. This from here to here is one edge. This from here to here is one edge. Okay? So there is no direct edge from this vertex to this vertex along this diagonal. So this is a simple graph, but this is a multigraph. Yes? So this is a multigraph. But this one is a simple graph. Okay? And that is another one. This is a famous graph called Peterson Graph. It's a nice symmetric shape. So you have a pentagon here and then a star inside and connecting each edge of these pentagon to this. So what you see here is called a Peterson graph, a diagram for the Peterson graph, because you cannot talk about the diagram. Now I am asking you, what is this number? So you learn that you shouldn't get confused. Q is always the number of edges, P is always the number of vertices. So if I want to calculate this quantity, this is just very simple. So 2Q minus P squared. So what is P is clear, yes? I have 5 dots as the vertices of my pentagon and 5 dots as the vertices of my star. So in total I have 10 vertices. So P is 10. But how many edges do you see?
I think I see 15.
It's 15, yes. So I hope that you are not confused. This
Also,
is
Mr.
one.
Babak, you wrote 5 and not 10.
So what?
I think you
Ah,
wrote
yeah,
5
thank you.
and not
Okay,
10.
thank you. Yes, this is 10. Yeah. The number of vertices is 10. 5 outside, 5 inside. Thank you. And then Q, this is 1, 2, 3, 4, and 5. This is 1, 2, 3, 4, and 5. This is 1, 2, 3, 4, and 5. So yes, 15. So it becomes 2 times 15. So it is 30 minus 100. So it becomes minus 70. So this quantity for this Peterson graph is minus 70. Okay. I want to stop here. We will continue the next part on Thursday. Is there any questions? No? Okay, thank you. See you later. Bye bye.
Hej, vad är det, Mr. Babak?
You're welcome. Bye bye.